Look up. We, as humans, are constantly reminded of the unyielding, invisible chains that bind us to the earth. Gravity. It is the silent, relentless force that holds our mountains, our oceans, and our very bodies in place. We are forever grounded, our destiny defined by the pull of a single planet. But then, there is the ant, the seemingly insignificant insect that scuttles across our ceilings, marches up our walls, and defies every law we thought we understood. It walks with a casual grace, mocking the very force that defines our world. To us, it's a simple sight, a tiny bug, a fleeting moment of curiosity. But beneath the surface of that casual stride lies a profound cosmic joke, a secret so elegant, so beautiful, and so logical that it could redefine our understanding of power and purpose. This is the question that lingers in the quiet moments of the night, a question we've all asked, a question that has no simple answer. How does an ant, a creature with legs so delicate they are almost invisible, walk on walls without falling to its inevitable doom? Is it a profound misunderstanding of the universe? Or is it something far more intricate, more brilliant, and more fundamental than we could ever imagine? The answer, we find, is not magic at all. It is a masterpiece of biological engineering, a perfect symphony played by forces so small they can only be seen with a microscope. The secret of the ant's impossible walk is not one single secret, but a complex, multi-layered solution that begins with the very ground it walks on, or rather, the very foot it walks on. To understand the ant's defiance, we must first descend into its world, a world where the laws of physics operate on a different scale, a world of incredible, unseen power. Let us begin our journey at the very foundation of the ant's miracle, its legs. 6 of them, each a marvel of biological precision. When we look at an ant's leg, we see segments. There is the femur, the tibia, and finally, the tarsus. The tarsus is a 5-segmented limb, and it is at the very tip of this tarsus that the true secret resides. The final segment of the tarsus holds a pair of sharp, curved claws, but these claws, we discover, are not the main tool for wall walking. They are used for gripping rough surfaces like bark or soil, providing a different kind of traction. No, the real magic, the true defiance of gravity, lies between those claws. Nestled between the claws is a soft, flexible, lobe-like pad known as the pulvillus. The pulvillus is a remarkable piece of biological technology. It is a pad of flesh that can expand and contract, and it is covered in an astonishing number of microscopic hairs. These hairs, known as setae, are the true heroes of our story. They are not like the hairs on our head. They are much more intricate, much more purposeful. A single ant's pulvillus can contain thousands, even tens of thousands, of these microscopic setae. But it is not their sheer number that is the secret. It is their very design. Each one of these tiny, microscopic hairs ends in a flattened, spatula-like tip. These tips, we discover, are the key to unlocking the ant's impossible power. They are designed to maximize surface area contact on a microscopic level. It is a testament to nature's profound elegance, a solution that predates our most advanced engineering by millions of years. But even with this incredible anatomy, the question remains, what is the force that makes these microscopic tips stick to the wall? The answer, we discover, is not a simple glue, but a fundamental law of the universe, a law so subtle it is almost invisible. To truly grasp the ant's secret, we must travel to the realm of quantum physics, to the unseen world of atoms and molecules. The force that allows the ant to walk on walls is called the van der Waals force. To understand this force, we must first dismiss the common misconception that it is a kind of glue. It is not. It is something far more beautiful. It is an electromagnetic attraction. Every atom in the universe, at any given moment, has a small, fluctuating electrical charge. Sometimes the electrons are bunched up on one side, creating a temporary, tiny dipole. When two molecules are close enough, the positive end of one is temporarily attracted to the negative end of the other. These forces, in isolation, are incredibly weak. But what happens when you have billions upon billions of them all working together? This is where the ant's pulvillus, with its thousands of setae, becomes a biological marvel. Each of those microscopic, spatula-like tips brings the ant's molecules into close proximity with the molecules of the wall. When an ant's pulvillus is pressed against a surface, those countless tiny tips, each one covered in billions of molecules, engage in this universal dance of attraction. The cumulative effect of all these incredibly weak forces, all working together at the same time, is a powerful adhesive force that is more than enough to support the ant's tiny body weight. In fact, studies have shown that the adhesive force generated by a single ant is so powerful that it could easily support hundreds of times its own body weight. This is the very same principle that allows geckos to climb walls and flies to walk on ceilings. It is a silent, invisible ballet of molecular attraction, a universal truth that we are only just beginning to fully appreciate and understand. But here, a new question arises. If this force is so incredibly powerful, how does the ant unstick itself? If it can support hundreds of times its own body weight, why doesn't it get stuck forever? The answer, we find, is another layer of the ant's remarkable design. The ant controls this incredible adhesive power with two separate mechanisms. First, there is a physical peeling motion. The ant does not lift its entire foot straight up from the surface, which would require an immense amount of force to break all those bonds at once. Instead, it peels its foot off, starting from one edge and rolling it away from the surface, like peeling a sticker. This allows the ant to break the van der Waals bonds sequentially, a few at a time, requiring much less effort. Second, the ant has a biological secret weapon. The pulvillus has tiny, microscopic pores that can secrete a special, oily fluid. This fluid, a mix of sugars and lipids, acts as a lubricant and a controlling agent. When the ant needs to reduce the adhesive force, for example, when moving quickly across a surface, it can secrete this fluid. The fluid acts as a buffer, pushing the molecules of the ant's setae just far enough away from the molecules of the surface to weaken the van der Waals forces, allowing the ant to move with incredible speed and grace. The ant, in effect, has a built-in control system for its own stickiness. The ant's walk is not just about its feet, it's also about its gait. When an ant walks, it does so in a highly efficient and stable manner. It uses what is known as the alternating tripod gait. The ant lifts 3 legs at a time, the front and back legs on one side, and the middle leg on the opposite side. The other 3 legs remain firmly on the ground, forming a stable tripod. This ensures that the ant's center of gravity is always supported, allowing it to move quickly and confidently, even on vertical surfaces or upside down. Its low center of gravity, combined with this highly stable gait, ensures that even if it encounters a slippery spot or a sudden gust of wind, it remains balanced. It is a perfect, holistic solution to the problem of defying gravity. The ant's secret is no longer just a biological curiosity. It has become a profound source of inspiration for human engineering. Scientists and engineers are studying the pulvillus and the van der Waals forces it utilizes to develop new, reusable adhesives. Imagine a world where we no longer need messy glues or tapes. Bio-mimicry, the science of copying nature's designs, is using the ant's foot as a blueprint for a new generation of robots that can climb walls to perform inspections or repairs, or even for medical applications where a gentle, but firm, grip is needed without leaving a residue. From microscopic hairs to an invisible quantum force, the ant's impossible walk is a testament to the fact that the most elegant solutions are often found in the most unexpected places. It shows us that to defy a universal law, you don't need brute force. You need a profound understanding of its subtle, hidden truths. So, the next time you see an ant scaling a wall, do not just see a tiny insect. See a masterpiece of engineering. See a creature that understands the universe in a way we are only beginning to comprehend. See the living, breathing proof that what seems impossible is in fact a beautifully logical reality.